So it's so great to be with you all here in presence at MOP. It's a great honor indeed to be giving this opening tutorial on the Jupiter's magnetosphere. And I have a lot to get through. I've got these 5 different topics that I've pulled together. And I've also noted that if you look and do a search on the word magnetosphere and Juno, you find in the abstract, you find 150 papers since Juno went into orbit around Jupiter. So there's a lot for me to get through, but luckily this is being recorded. And so the thing we've learned from the Zoom period is you can go back and you can look at all of these recordings at your own pace many times. So if I go too fast, you can always go back and try and understand what's going on. So I've picked up these 5 different topics, and what I want to do is to go through them and talk about what I think of the main issues that we have been addressing with Juno, as well as the things that we could do more with Juno, as well as other things to model relating to the data. So let's start off with, let's try this. No, that doesn't work. Let's try this. That does work. So it's a very basic introduction to the vast magnetosphere of Jupiter. Very strong magnetic field leads to a large volume of magnetized environment around the planet, many times that of the Earth, and its rotation dominated with a 10-hour period. And indeed, a major issue relating to its large size is the fact that EO dumps out a ton a second of sulfur and oxygen. But most important, and something I want to emphasize in this talk, is that this is inflated by hot plasma, and the fact that the plasma pressure is very high, dominating over the magnetic pressure, is very important at Jupiter. So we've flown through with a Juno spacecraft for the past 6 years. We celebrated last week, 6th anniversary, and you can see, compared with the human there, how large the spacecraft is. It would barely fit in this hall, I believe. And all of the 9 instruments on board have contributed to the magnetosphere in many ways. I'm trying to understand what's going on. The orbit, of course, is key to understand what's going on. And if you look at, we chose an orbit that was above the clouds and under the radiation belts to avoid the damaging effect of the radiation on the spacecraft. But because of the oblateness of Jupiter, you have this precession of the orbits from above to below the equator. Now we hope to have 75 orbits in total. If we look at how these orbits have evolved, what's interesting is that you can see that we've evolved from going from dawn side around to, dusks, from dawn through midnight to dusk side, and will orbit around towards noon. But very interestingly, because of this precession of the orbits southward, looking here in the orbit plane, perpendicular to the orbit plane, we are now moving into an era when the equator crossing will move past the orbits of the satellites, where we cross the orbits of Callisto and Ganymede already, and then we will be crossing Europa and Ganymede pretty soon. So this is the future, with the rest of the mission going through, we hope, September 25, hoping that the radiation does not cause too much damage. Now, what I'm going to do is to go through these different topics and discuss at a very high level, because this is a tutorial, but we will hear many more things in the meeting about these topics. And I want to talk about, first of all, the very global structure, and these cartoons at the bottom are going from Vitenis's 1983 through to the modern, some recent cartoons. But of course, as things get more complicated as we get closer, as we shall be discussing this week together. Now, very importantly, the Juno spacecraft has passed through the magnetopause, had many crossings here on the dawn side, and is now being crossing again on the dusk side. And this is from a poster that Rob Ebert is going to present later today. It's a work in progress, trying to work out how much the flattening, this is a model that Mariel Desroches did for her thesis work. But the idea is that because of the inflation at the equator due to high beta plasma, there's a flattened magnetosphere, the wrapping of the interplanetary medium around the magnetosphere. So we are now beginning to get some more measurements from Juno on this. Another issue is what the boundary is like and what's happening on the boundary layer. There's a lot of work being done trying to understand the interaction of the solar wind and the interplanetary magnetic field with the planetary magnetic field. And there's lots of issues here related to what's going on the boundary, trying to understand the shear instabilities, Kelvin-Helmholtz instabilities, but also to try and look at the small scale intermittent reconnection that must be happening here and what impact that has on the magnetosphere inside. And one of the major issues is what's happening with the pressure balance between the hot plasma on the inside and the round pressure on the outside, involving indeed the intermittent reconnection. So there's some debate. Vitenis coined this term cushion region for this boundary layer. There's a good question about how the pressure is in fact maintained, pressure balance is maintained in the outer magnetosphere, and whether or not this cushion region actually exists. So we are going to have much discussion about whether or not the magnetosphere is open or closed. And I see this conversion from PowerPoint to Keynote has led to some disappearance of some words, but never mind. The important thing is to try and understand what is going on in the polar region and how much of the flux coming out of the magnetosphere. And I included Tintin because of the tuft of his hair, reminds me of how much of the tuft of magnetic field comes out of the magnetosphere and where does it go? Does it spread out into the magnetosphere? Does it connect to the solar wind? These are the major topics that I'm sure we will be discussing at this meeting. How much material crosses in and out of this boundary layer, and what is the contributions to the magnetosphere of material from the solar wind, and how much escapes? So the next topic I want to talk about is to talk about the plasma and current sheet in the middle of the magnetosphere. And we'll discuss these plus the radial transport and material loss down the tail. So first of all, let's talk about the disk structure. This has been nicely revealed by Juno's crossing of the current sheet put together by Jack Canerney in his modeling of the current sheet. And you can see that we have a strong azimuthal current in the equator, a weaker radial current, and it varies by a factor of 30% orbit by orbit. These are the different magnetic field strengths in the north, the azimuthal and radial currents varying orbit by orbit. Now, when we look at the plasma sheet, what we see is considerable variation as the spacecraft, as the centrifugal equator flaps over the spacecraft, and so we see these pulsations of the plasma mapped out to make the plasma in the centrifugal equator, varying by a factor of 2 between orbits. Now, what's very important is the heating of this plasma as it moves out, as presented in surveys of the magnetosphere. And indeed, the very issue of how the plasma heats up as it moves out through mechanisms that we now know is probably related to turbulent behavior in the magnetosphere, and then heating up adiabatically as it comes in, maybe accelerated in the dipolarization from the tail. And I'm glad to see that Joachim Sauer will be giving a tutorial review of this topic of heating in the magnetosphere later in the week. So when we think about radial transport, which is very important to try and understand what's going on, the traditional picture of flux tube interchange explaining that if you have more material in flux tube A than B, they will interchange. And this has been described quite effectively using a diffusion description. And it's limited by the connections at the ionosphere, up here by ionospheric conductance. But you need communication between the ionosphere and the magnetosphere for this to work. And this has been well described quantitatively and surveyed from Galileo data. But what happens at larger distances where the field lines are stretched, kinetic effects become important, and communication with the ionosphere begins to break down. And so what we have to think about is as the plasma beta begins to become large, we have to worry about the ballooning instability or other effects of kinetic effects that could be occurring in the disk that leads to radial transport. And this is an issue that is not understood. This is something that we really need to work on and try and understand how the plasma transports radially outwards. So, and indeed, what can Juno tell us about these processes? So let's think a little bit about radial transport. Velocity is hard to measure directly, but if you take a description, this comes from work that Chris Russell showed us how to do, and you can then derive, if you have a mass production at EO, you have a radial profile that's measured of density, you can then derive a radial flow outwards. And the amount of speeds are quite small, 20 to 100 kilometers a second, moving out in a time frame of weeks or months. And the net result is that you can then derive a outward radial transport. Now, in reality, we need to find out how variations in the plasma distribution, plasma production, and the radial outflow vary. And we need to make more measurements of this. So Juno can tell us a lot about this, I hope. Similarly, understanding how plasma is lost, there have been measurements previously in the tail of flux tubes going down the tail. This is a more recent study using Juno observations by Marissa Vogt in 2020. Lots of large events going down the tail. But the big question is what is happening on the dawn sector? We see, sorry, on the dusk sector. We have observed them on the dawn sector, but not so much down here. And this is where we believe there could be more kinetic effect, small plasmoids going down the tail, or some other more kinetic processes. So then we need to think about what's going on at EO. And here I want to emphasize in this plasma interaction that chemistry is very important. So if you look at all of the different moons, different kinds of moons, different kind of interactions, we'll have lots of discussions of this later in the week. But I want to emphasize that when you look at these interactions, you have to think about not just the electrodynamic interaction, but also the chemical interactions. And indeed, what you see is that there's a whole load of chemistry involved with the plasma interacting with the SO2 atmosphere at EO and the oxygen and hydrogen atmosphere at Europa. And including this chemistry is very important in really understanding this interaction. And we will be making measurements with Juno in this environment in the next couple of years that will help us test these ideas. Again, when we think about the neutral materials that are ejected in the interaction and going out, to make these, the neutral clouds, And then when we look at the eoplasma torus, we have to include the chemical reactions and the energy budget when we understand to understand the torus and put this together. And again, these will be tested with the Juno flying through in the next couple of years. Now, we've flown through with Juno the EO flux tube, and there have been studies of how this varies downstream of EO. And there's going to be a tutorial by Jamie Soleil, who will discuss this in more detail throughout the week. I want to move on to an issue that to emphasize that there's a temptation in our field, whenever we see variations in the magnetosphere, to say, oh, that's EO, eruptions, volcanic eruptions on EO. But if you look and think about it, the volcanoes that we see on EO, yes, there's an atmosphere related to those volcanoes, but also sublimation of the surface. We see variations in the neutral clouds, and we see the torus. But over the past 20 years or so, there have only been two large eruptions, one at the time of the Cassini flyby and one during the early part of the Hisaki period, where there was a factor of 3 increase in the production of material at EO. So the question is, what kind of volcanism produces these big variations, these perturbations, and how does that work? So there's a lot of work to be done looking at EO and trying to understand the consequences of that. So now let's move on to the aurora. And here there's a lot of papers that have been published on a whole variety of different topics. I will try and talk a little bit about the structures. Will be reviewed in a tutorial by Bob Lysak. So if we think about the all of the different, this is, sorry, got distorted in the conversion, but we have all the different instruments as well as observations from the ground have been observing the aurora. This is a lovely HST image movie from Johnny Nichols showing various activities in the aurora. So these collaborations between observations from Earth observatories as well as from Juno have been key to trying to understand what's going on in the aurora. So basically what we have with the aurora is a system that's coupling the rotation of the planet to the magnetosphere and causing the magnetosphere to rotate. And indeed, we understand there's some co-rotation breakdown that occurs, but the question is this due to ionospheric conductance or electrostatic potentials or something else we don't quite understand? And indeed, the Juno observations of the magnetic field has shown us that these currents are these enforcement currents are, they are weaker than we expected and more filamentary, and they seem to be asymmetric and variable. So there's a lot of work to be done in trying to understand what's going on here. Similarly, when we look at the auroral emissions and try to understand what is causing them, there's a lot of work to be done trying to understand basically the sort of average behavior of the aurora. The main aurora with the zone 1, the upward currents, and zone 2 downward currents, and what is causing those and what the processes are. And we're coming to the viewpoint that there's less static potentials at high latitudes, more turbulent behavior producing broadband structures. There are also some variable structures that are important and interesting. One is the dawn storms, probably related to plasmoids going down the tail, dipolarization causing acceleration of particles. And then we also have those particles being carried in towards the planet at lower equatorial regions, producing diffuse injections in the diffuse regions equatorward of the main aurora. And these we're combining in situ measurements with remote measurements to try and understand what's going on here. Why is this not working? Oh, your computer wants to shut down shut down. Don't think we want to do this. Let me hit cancel. Okay. I must have hit the wrong button by mistake. Okay. The acceleration process is complicated. It's very interesting. And I'm looking forward to the review, the tutorial review by Bob Lysak. Now, one of the big issues that I mentioned is the whether or not the magnetosphere is opened or closed. And indeed, the many observations of X-rays over the past few decades have been pointing to this issue and raising the issues whether or not the polar aurora are related to an open flux tube. That's the Tantan tuft area that I mentioned earlier. And there is evidence of heavy ions suggesting that it's coming from inside the magnetosphere, but at the same time, when we try and map from the polar regions to the out into the magnetosphere, there's a lot of difficulties trying to work out where these polar aurora are connected to. So this is a major issue of discussion that I'm sure we're going to have. When we look at the Juno UV observations, Juno, unlike Hubble, gets to see on the midnight side. And what Juno has shown is that on the midnight side, there seems to be a disappearance of some of the polar aurora. And this leads to a question about what is controlling the polar aurora, and why does it disappear over the night? And where is this material connected to? When we look at the radiation belts, my last topic, these have been observed for a long time. And when we're looking close, not only do we have to think about these radiation belts trapped in close to the planet, but we also need to think about the ionospheric structure. And I point out this new review paper that Michael Mendillo has put together, reanalyzing earlier missions of the ionospheric structure, and there's huge variability. So we have a very messy situation in close to the planet, not only with the radiation belts, but also the complexity of the ionosphere, a topic that we will be spending more time on, I'm sure, in the next few years. Of course, understanding the magnetic field has come from multiple flybys. The more you look, the more detail and structure that you see, and more detailed structure. And this is very important when we get to think about the ionosphere, because we're worried about how do you trace along magnetic fields when you have this complexity of the structure. And so when you try and interpret observations of ions, electrons, and indeed using the waves that Bill Kurth will be talking about later this week, it's difficult to try and understand what's going on in the ionosphere. And I'm pretty sure that's going to be a major topic this week. So we will also have discussions of the radiation belts and what we're discovering with Juno, with multiple instruments measuring the radiation belts up close. So I'll just end with showing you the last phases of the next few years of the Juno will be coming in close. And you see here we have about 30 crossings of the Eoplasma torus, which will be very important in situ measurements that will be made at the same time as people having ground-based Earth-based observations. So what we would really like is for EO to erupt now. So I propose at some point we have an EO dance where we all jump about up and down and get EO to erupt, please, now. Leave you with 4 big questions. These are the ones that I think are the biggies. One is the issue of how the volcanoes work on EO. Next is the mechanisms for radial transport. I think a lot of work to be done in trying to understand that. There's an issue of what causes the variability in the auroral emissions, the role of the solar wind, the EO production, and the thermal pressure in the magnetosphere. And then the last big one is this issue of how open is the magnetosphere, and what can Juno data and the models tell us. And with that, I'll thank you very much.